Well, with no further ado, let me introduce Dr. Tom Coughlin, President of IEEE USA, also President of Coughlin Associates and IEEE Fellow, and he will give you more details about his background as he comes to the podium.
There you go. Thank you, Michael, for inviting me here, and thanks for having me here. So I'm going to give my talk on memories of tomorrow. So, and he gave you some information on it. So I don't really want to go through this. You can look at the slides later. But I write things. I do consulting. There's a couple of reports over there that, if anyone's interested in them, on storage for media and entertainment, also emerging memories. I've got some flyers in those there, and I've also been involved in doing events of various sorts. But let's talk about what we're going to look at tonight. So we're kind of in a very interesting time when you've got sort of a Cambrian explosion, if you will, of different ways in which people are finding to be able to keep stuff, whether it's be temporary or for long term. And so we'll talk some of the drivers that are enabling these technologies to come about and driving our demand for content, and look at particular technologies such as hard disk drives, flash memory, solid state drives, and then look at some of the things that have been going on in terms of protocols to replace some of the older SCSI, SATA, for instance NVMe, working over the PCIe fabric. So some people say they don't want some of the acronyms are too much. Non-volatile memory express is what NVM stands for. Okay, NVMe, PCI is a common interface and a bus in the computer. And then we'll talk a bit about some of the new emerging memory technologies, which I'll put them under the category of persistent memories or non-volatile memories, which could replace or serve functions different from those that volatile memories that we use. Some conclusions and some references. So I'll bet this is the clicker. So first of all, let's look at some of the things that are driving people requirements for more stuff. So memory and storage needs, basically, you could say it's exploding. There's an update of an IDC report that they did saying that by the amount of data created by 2025 be something like 175 zettabytes of data. So that's a lot of data. It's like 10 to the, I think that's 10 to the 21 if I remember. No, it's 10 to the 20, it's up there. And there's 31 zettabytes right now. So there's 31 zettabytes created last year in 2018 according to their estimate. So where all this is coming from is a lot of unstructured data. A lot of it's just coming off of sensors and devices that are connected, IoT type applications, development of genomic research, big data, whether it be telescopes, big science experiments, oil and gas, all sorts of things, and just in general, all the cameras and things like that, and the social networks and information is gathering in various ways. So there's going to be growth as a consequence of that. Local storage at the edge. Some people call that the fog, just to kind of create something that sounds sort of like the cloud, only it's closer, right? And also, there's a need for different types of memory or storage for fast processing of data, as well as keeping the results of that data for either a medium period of time or even for a long extended periods of time. And of this, say 175 zettabytes that are created, for example, this chart over to the right-hand side there shows that only a percentage of that data is probably going to be kept. So mostly what this data is about is machine-generated data that has to be processed right now to have value. For instance, if you got an autonomous car, you have all these sensors in the car. You want to fuse all of the information from all those sensors and cameras and make a decision right there. So the data doesn't have a long-term value; it has a value for that mission-critical application. So the result is that probably only in the neighborhood of about 2 to 3% of all this generated data is going to be kept long-term. But all of it, if it's going to be useful, is going to be used in the short term. So a lot of requirement for fast memory to support that, and then a requirement for stuff to keep whatever is left over, or whatever we keep in the future for the long term. So an example of how some of this stuff is is increasing in size. So I do some stuff in the media and entertainment space in terms of looking at storage requirements. And this is some uncompressed storage requirement capacities, just examples for professional media standards. And if you look, we're down into 8K sort of stuff now, and 8K ultra high definition, for example, may use more than 170 times the capacity of the high definition, and a considerable amount more than the 8K. So these things are becoming big. They're higher frame rates generally as we go to the higher resolution to avoid motion artifacts. The people are putting more bits per pixel in order to be able to get higher dynamic range and other characteristics. And then also people are doing multi-camera projects now. For instance, 360-degree video, they're capturing a lot of cameras at once, high-resolution cameras, and they stitch them together. So there's processing and just an awful lot of data that's being created. There's even talk of going to 16K. In fact, 16 by 8K is about right if you want to get something that's this close to your eyes for doing a 8K per eye. Okay, so 16 by 8K. So this stuff gets big fast. In fact, if you were to see how big this thing could get, one of the things I've been saying for a while is I think we're just a few years away from seeing video projects that can be approaching an exabyte of total content generated. Here's the example. Let's say 16 by 8K pixel resolution, 24 bits per pixel, 300 frames per second raw video content. That require about 115 gigabytes per second data rates, which we don't have pipes to do that right now. 414 terabytes per hour. So if you had 4 cameras then to try to get something that gave you some three-dimensional view, then the raw data would be about 1.66 petabytes for an hour of content. So if you capture a few hundred hours of content, you've got a lot of stuff. That's why I'm saying I don't think, for a big project, of course, expensive, but we're not too far from people being able to generate this in the course of, say, video type projects, say within 10 years. Hundreds of petabytes of data and even approaching an exabyte. So personal devices capturing more details in our lives than ever before. People are using cameras in stores to figure out what things you're interested in or to find your responses and stuff. There's this all manner of both industrial and even at your home, in home applications where we're creating connected devices that can sense things, that can interact with you, perhaps help with our health care, keep people safe and able to live independent lives longer. And our consumer electronics connected applications find your way, connect to this, maintain our health, make the world a better place. Everyone, you all know, people are talking about building. In fact, I just actually bought my first new car in like a long time. And it's got all kinds of bells and whistles on it, all this driving assistance capabilities on the thing. And that stuff is getting more and more sophisticated. I was actually at the GPU Technology Conference, which is still going on up in the Bay Area. And there's an awful lot of work going on in creating autonomous driving and driving assistance of various sorts, creating algorithms for, I think one thing they called it was a force field, a safety force field to help to make good decisions around cars around you. So all these things are being enabled by intelligent machines, applications, and then the ability to capture content and then process it. And speaking of cars, it's kind of an old quote at this point, but Google autonomous car estimate generates about 1 gigabyte per second. Average driver today at least drives around 600 hours a year, so that'd be about 2 petabytes per car per year. Number of cars worldwide estimated to surpass 1 billion. So the potential size of content generated by, for instance, connected smart cars, at least generated by them, is pretty large. So a lot of this stuff, of course, is immediate processing. It's just for machines to communicate with each other and make decisions based upon that data. But some content kept for the long term, some that goes in the cloud, where you might do a bulk of analytics, for example. So looking at some of the devices that we have to be able to keep this stuff, going from the right-hand side here, we got things that are on the memory channel of computers, which are really fast, like it's 10 to the 7th data rates on them. And then if you go into PCIe bus type devices, you're down maybe an order of magnitude in the speed. NVMe is actually, a lot of NVMe products are built around the PCIe bus. And then if you go into some of the traditional storage devices, the SATA and SAS, you're down maybe another a few orders of magnitude below those. And then we go into hard disk drives, which have inherently generally a slower performance. Then we're down another 1 or 2 orders of magnitude from some of those SSD type devices. So this is kind of a frame of these things. Now the interesting thing about this is generally as we move again from the right to the left, things get cheaper. So hard disk drives are good for stuff, they're not as fast, but they're fairly cheap in terms of dollars per gigabyte. So if you're keeping a lot of stuff, at least your initial costs for buying that memory are fairly low. As you move up, say into the memory channel, then you've got things that are very fast, but they also tend to be relatively more expensive. So people, the immediate processing goes in the fast storage, on this fast memory, fast storage, and then the stuff that isn't kept as long goes in hard disk drive, or even what I don't have on here, which is magnetic tape. There's people that keep that for long-term stuff. It's still around after almost 70 years. Here's a view, some different views of what's often called memory or storage hierarchy here. On the right-hand side is I have a colleague, Jim Handy, and this is something he's been doing. He's got log scale price per gigabyte on the horizontal scale in the bandwidth, the data rate of these devices on the vertical scale. And so he's showing, for instance, the cache in the memory, in processor devices, different cache memories. Then you got DRAM, SSDs, hard disk drives, and magnetic tape. So it gets cheaper as they go that way, but the performance generally goes down. And the point being made in this particular chart here is that there's gaps that sometimes open up between these technologies. For instance, between DRAM and SSD, there's an intermediate state, and the slide on the left shows Intel's Octane 3D cross-point memory, which is a phase-change memory device, which has a speed which is intermediate between, in terms of performance, between DRAM and solid-state drives or flash memory, and also has a higher endurance than the flash memory, so it's kind of fitting into a niche in between those two things. So that's an example of developing some of these different approaches of looking at the way we use memory and storage and the different uses which they have. So the general fast is great, but fast is often more expensive. And so in designing systems, oftentimes people use more than one type of memory to help to make their device useful, but balancing off performance requirements versus the overall cost and the amount of information you need to keep on it. And it's also true in data centers as well. So let's look at some of these particular technologies. First, hard disk drives. Hard disk drives are, what is it, 62 years old now, 1956. They're currently shipping, they start out at 5 megabyte for 52-foot disks in a box back in 1956. They're currently shipping 16 terabytes in a 3.5-inch box with 20 plus terabytes expected by 2019. Both Seagate and Western Digital said they're coming out with products in this range. And current aerial density is exceeding a gigabit per square inch. For a lot of these products now, especially the most popular type of hard disk drive right now, which is high capacity hard drives going in the data center, they're actually building these hermetically sealed, filled with helium. That's going to last for 5 years. Anyone who's worked with helium, that's pretty daunting. But they're actually been shipping these now for several years now. The advantage of helium is that the density of helium is lower than air. It causes less flutter with the rotating disks. They can actually make thinner disks and have them operate. They can pack more disks in a package, and therefore that's one way of getting higher capacity. They also, the helium extracts heat better than air out of the device, so actually run cooler and as a consequence use less energy. So there's less friction, less energy from the rotating disks. So fastest growth in hard disk drives, again, is for essentially for bulk or nearline, whatever you want to call it, storage in a data center. That's the biggest growth area right now in hard disk drives. Besides tape and optical disks, hard disk drives most cost-effective storage for colder data, and it has a fast, because hard disk drives are generally always connected and generally are rotating and ready to go. You can get your data fairly quickly from it. In fact, let's see, do I have it here? I may mention it later on. If I do, then shame on me. But there also are people that are both Seagate and Western Digital. Seagate's talking about introducing a dual actuator 3.5-inch hard drive for data centers this year. They're apparently sampling this now. And at the OCP, Open Compute Platform Summit last week, Western Digital is also showing a dual actuator drive. It roughly doubles the data rate out of the hard drive by doing that. Essentially, you got two independent actuators on the same rotation, and they're driving independently, and they can essentially read twice as much data off at a time. So here's my projections on by applications hard disk drive, high, medium, low estimates. The peak actually in hard disk drives is about 2010, and since then there's been some ups and downs. There was a big flood in Thailand in 2011, which impacted drives in 2011 and 12. But since then, the decline's been seen from about 2014 have been due to erosion solid-state drives taking the place of hard disk drives in a lot of applications, such as notebook computers and things like that. So over to the right is estimates actually going forward of a low estimate, a median estimate, a high estimate, and the fastest growing category here, the big growth area for hard disk drives seems to be in this high capacity, low cost storage device running at 52, but more often 7200 RPM that's in a data center. And so that's kind of where the industry has a lot of focus on doing that. And some interesting technologies in terms of what they're looking at doing there. This actually is from a Western Digital event I went to a few weeks ago, where they were showing growth in what's called shingled magnetic recording hard disk drives. Now what this is if you know, hard disk drives are laid out with tracks on the disk. So in shingling, what they do is like shingles on a roof. They write a track, and then they partially overwrite it with another track. They partially overwrite that. So they get effectively a higher track density, and therefore more data on the drive in doing this, which is great, except if you want to write again. Okay, and you've got data on the track that you want to keep. Now you have to move that data, and you've got to write over the old data. Okay, so it creates a lot more overhead for the write process. It's actually a little bit more like what flash memory does in writing, erase and then write cycle in flash memory. So it's great if you're writing once and reading many times. So it's a great worm technology, write once, read many times. And if you actually look at this chart here, the one on to the left there, total exabytes shipped. This is again for the data center applications. That orange part of the bars there is what their estimate for the shingled magnetic recording versus conventional magnetic recording, where they're not doing shingling. So they're actually seeing a lot more application for these, what would be sort of a worm type device, more for a colder storage where I'm not going to write very often. They see the biggest drive there. Now the other thing that's going on is there's hard disk drives are using a technology called perpendicular magnetic recording, where they're recording the bits in and out of the plane of the film, so normal to the plane of the film, up or down. This allowed them to go to higher densities in the old longitudinal recording where the bits were in the plane, but it sort of reached the limit of what you can do with that alone. So they're now looking at technologies that will get you smaller bits, and to get smaller bits you have to get bits that have a higher coercivity. They have to be stiffer. They have to resist the ambient thermal fluctuations in the environment that cause random reversals. So they have to have a higher coercivity media. But the higher coercivity media is harder to write on with conventional magnetic heads. So the technology that people are working on is to go to these really high coercivity media that'll be stable for long periods of time. They're going to use energy-assisted magnetic recording. Now this means that I'm applying some energy to kind of soften up the coercivity, if you will, of this magnetic media, so I can write on it with conventional heads. There's two technologies that are working at doing this. One is called heat-assisted magnetic recording, where they're using lasers to physically heat the media up and effectively lower its coercivity, so I can write on it with a conventional recording head. The other technology is using what's called microwave-assisted magnetic recording, where they're actually using a spin-torque oscillator that's built into the write structure of the head. If anyone knows what these things look like, this is pretty incredible. They can do this stuff. Western Digital has been promoting this idea of doing this microwave-assisted magnetic recording. And they're using part of the Damascene process they're using for making the heads, that they're able to get this tiny little quantum mechanical device, a spin-torque oscillator, in the write structure of the head. So both Seagate with the hammer, and that's the heat-assisted, and WD with the microwave-assisted, or MAMR, they're both talked about having products available at least for qualification purposes this year with these technologies. And again, I said before about the dual actuator, that both companies are also looking at making these dual actuator drives, which will increase the throughput. The reason why this is especially important to increase the throughput of these drives, if I start to get 20, say to 40 terabyte hard drives, unless I increase the data rate out of it, if I have to rebuild that thing, for example, it takes forever. So by increasing the throughput of the drive, you can make it a more useful device, if nothing else, to rebuild in an array, for example, or to be able to get data on and off of it. In fact, one could conceive of the possibility of having a device that is so big that if its data rate wasn't high enough, you could never write on it during its lifetime, or read all the information off it during its lifetime, which is kind of an interesting paradox, isn't it? So those are some of the things that are going on. Also, if we look over here on the right-hand side, this is WD. They were saying 2019 they're going to be 16 to 18 terabyte energy assist, which I think is going to be MAMR. And then they're looking at 20 plus terabyte drives with dual actuators by 2020. So that's kind of what's going on in the again, for this high capacity, low cost storage in the data center. There's a roadmap. This is the ATSC, Advanced Storage Technology Consortium roadmap, which all the hard drive guys and a lot of component guys for hard drives belong to. They haven't changed it since 2016, but they're showing advances somewhere out beyond 2025. I said before, they're currently about 1 terabit per square inch areal density, a little bit more than that. They're talking about getting up to 10 terabits per square inch, which is like a 10x increase, roughly, in the areal density on the drive somewhere beyond 2025 or so. So anyway, this is a little bit more on some of these technologies again, and we're going to have bigger drives for whatever you use it for, backing up your stuff at home or especially in the data centers. So that's hard drives. Let's talk about flash memory and solid state drives. So flash memory, of course, is a semiconductor technology. It's a non-volatile memory. Hard disk drives are non-volatile too. You can turn the power off, the data's still there. The same thing is true in flash memory. So it's been increasing in storage capacity and decreasing in dollars per gigabyte. A lot of that is because the factories to build these flash memory is very, very expensive. The 3D flash plants are about $9 billion or so to build these things, and they probably spend $1 billion a year with new equipment to keep it up to date. They're still more expensive than hard disk drives. That's because the volume's up. Amortization of the cost of the factory is it's gradually going down as we build more of these, and also as we build more density per die. So it's as it does that, it's winning more applications, for instance, versus hard disk drives, but also opening up new types of applications too. So development of interfaces that are built around the characteristics of solid state storage, particularly this NVMe over PCIe interface to replace SATA and SAS, is allowing big increases in terms of performance, roughly a 10 to 100x increase in terms of the potential data rates out of these devices. There also is work going on to do this NVMe transport protocol over fabrics. And this has been InfiniBand and Fiber Channel, but there's a lot of work, and people now, a new standard, and I'll talk about that a little bit later, of doing this over IP-based or Ethernet-based networks as well. So some interesting stuff there. So now in many data centers, flash memory, in many data centers, many applications, flash memory is now the primary storage. It's the storage for the stuff that you're doing immediate work on that isn't in memory yet, okay? And then hard disk drive is behind that for the stuff that you want to keep fairly good access to, but it's not as important, and you're not going to overwrite it and change as much. So flash memory also is more rugged. It can stand more shock and vibrations than hard drives, so it's also favored storage for remote locations, like edge storage or things like this. These things are full of flash memory. So in terms of expectation, what's going on in flash memory, here is a interesting chart on the right-hand side from Tech Insights, where they're showing the major flash manufacturers and their view of the transitions. Back around 2013, let's see, I think it was 2013. Samsung introduced their first 3D NAND, back around 2013. About 2014, 15, they started to actually ship product. Since then, the other major flash memory manufacturers going from a planar process where they're just building cells in the plane of the wafers. They're actually building stacks of cells, memory cells, on top of each other. And currently, people are shipping up to 96 layers of flash memory cells in stacks. which has allowed them to increase capacity by doing that. So also they had to build new factories to make this, those $9 billion fabs. And basically, people talk about doing that, building these 3D flash fabs, actually getting the yields up. Basically, they finally reached parity sometime last year in terms of the number of 3D flash made versus the planar flash. The planar flash is running into problems because it's based on the same kind of lithographic shrinkage that sort of killed Moore's law. That it was really hard to get below 15 nanometers to get a functional device. So instead of doing that, they relaxed on lithographic standards, and they're like somewhere between 30 and 60 nanometers, and they just built these big stacks. So they're currently shipping 96. Last year, Samsung was or actually this year, WD talked about 128 layer, and there's actually been papers at some of the conferences talking about 500 or more of these NAND cell layers. So these things are turning into skyscrapers on the wafers. Pretty interesting. So they're shipping 64 layer in volume now. Some folks like WD are saying they're shipping 96 layer. And the price reductions, of course, although the return on the number of layers gets a little bit harder because you have to do a lot more fabrication on the wafer, it's still giving some incremental price. As they get more layers, it gives you an incremental price decline on there. So the price per gigabyte continues to drop. Now here's some of the other things they're doing. A lot of the original flash was 1 bit per cell. What's called MLC flash is 2 bits per cell. That's multi-layer cells. It's actually 2. And that's been very popular. There's products out there now, especially consumer type products, or a lot of your flash memory sticks or SD cards, things like that, that are either 3-level cell or some are even 4-level cell. Now, generally what happened is, as I would increase the number of bits per cell, my endurance goes down. Roughly for every doubling in the number of bits per cell, you go down about a factor of 10 in terms of the endurance. So your USB stick or your flash memory card, you're not going to write on that too many times before it's not going to work. Maybe 100 times or something like that. But that's usually what people end up doing on these things anyway. What's happening though with these 96 layer flash, they've got a 70 nanometer, I'm sorry, it's actually 70 nanometer minimum feature size. As the feature size gets larger, they have more endurance. You can write on them more often, so they're actually looking at that as a way to enable making quad level cells and using them for more consumer, perhaps even enterprise applications. I'll get back into somebody else doing some of that a little bit later. So that enables a relatively durable 4-bit per cell, which also helps to lower the cost, right? Get more bits in a given cell, plus they got lots of cells. So they're also, some of the newer devices are coming out where the different parts of the flash memory die can actually have different cell configurations. For instance, I could have some high endurance SLC flash as well as a higher capacity QLC flash with lower endurance for doing different things. And so there's even tiering is talked about within technologies such as flash memory and new devices. Some interesting stuff. Again, this is from this WD storage field day I went to. This is the top chart here at the top was looking at the these different 3D NAND nodes, and the vertical axis not labeled there is the cost. So it's the fab cost going down over time, going to these higher level. They can get actually ultimately when they go through the yield curve, they get the volume up. They can actually get the net cost down to manufacture these things, therefore lower price per gigabyte at a point where the new technology, like the 96 layer, drops below the prior technology, the 64 layer. Okay, and that's what's as you get the volume up. Ultimately, you get to this point, you get to an even lower cost, total cost per bit sort of level than you were before. So it's an interesting thing about why they're doing this. There also is Intel introduced their 3D crosspoint technology, which is sort of faster than most NAND is and has a higher endurance. What a lot of the flash guys except Intel have done, and WD is one of these, they introduced what they were calling a high performance flash, which is probably SLC flash, which has higher endurance, higher performance. And so here's this, the traditional NAND here, and what we're showing here is the access time, the time to data, and the die cost. And they actually made a specialized flash going for the high performance here, so it has a higher die cost, but the access time is a lot faster. It gets faster as it goes this way, okay? And here's a hard drive here. So hard drive NAND and this LLF NAND that they're talking about. And besides Toshiba, there's other companies besides WD and Toshiba, who share a fab, there's other companies that are doing these approaches as well. So it's kind of competition potentially against the 3D XPoint technology using NAND, or something approaching that. So looking at SSDs and hard drives, SSDs are faster on the read and write speeds, often called bandwidth or throughput. They have lower latency, that is time to get data from when it's requested, than hard drives. They can complete more operations, IOPS per second, than a hard drive. They generally consume less energy. They don't have moving parts. And hard disk drives continue to spin the disk. They're more rugged, so they're useful in some of these edge applications or in your phones and things like that. And so those are the advantages that they have, but they're more expensive, and so it's those decisions on performance and these other characteristics versus the cost of the storage that is some of the drivers of when people use one versus the other. Now, just to show sort of an average, looking at the cost of hard disk drives and SSD, at least if they can introduce these energy-assisted magnetic recording technologies, we'll probably see a similar sort of decline in price of the more popular hard drives. This is the native capacity, not compressed or anything, versus flash memory going forward. But if they don't get the energy assisted, then that may be a very different step. Currently, hard disk prices for a gigabyte as low as 3 cents a gigabyte or $30 per terabyte. NAND flash prices can be as low as 0.25 cents per gigabyte, and I think with the current excess capacity, it's probably going down a bit from that even. It's about eight times higher than hard disk drives. So let's talk a bit about what's going on in these now with these new interfaces built around the performance characteristics, solid-state storage, and also about building fabrics with these. So one of the things that has happened with non-volatile memory is as we've gotten these faster non-volatile memory devices, especially moving to NVMe running on PCIe, all the software that is the drivers and has started to show up as significant factors. So here's for instance, a PCIe 4 Gen 3 device here. This is looking at a bunch of the software stacks here, and then the device latencies here. And you can see that becomes actually the minority problem versus the software. So it's been a major effort with groups like Storage Networking Industry Association on making new capabilities that will reduce some of that software overhead. And basically, one of the things is, especially moving into persistent memory, we need to look at moving away from a storage versus memory approach, perhaps having the capability of storing at the byte level, not blocks. Avoid the storage stack altogether, and avoid things like flash translation, which actually made originally so that SSDs could emulate hard drives. So it's led to looking at software and other operating software and other things that could more easily support different ways in which we can use these memories, and ideally even where we can have direct access from the memory to the actual persistent memory device. So that's kind of the holy grail where this is going to, new ways of accessing data for processing. And then the idea that, like other protocols in the past, that we can then extend this over fabrics, so we can actually have boxes in a storage system that could be communicating with each other. There's these fairly fast data rates. And there's things like that O should be small but rocky, RDMA, where you can do RDMA, direct memory access is what that stands for, over things like Ethernet and that sort of thing for memory-like data access. And these emerging memories could enable that, and some of these even at byte type level versus a block or a page level, like with NAND flash. So there's work, this is one of the important characteristics needed to enable these technologies. This NVMe, actually I saw a more modern version of this yesterday. I was at the NVMe Developers Day in San Jose. Actually, it's Fremont, excuse me. But there's a group there that's developing this NVMe standard. And this year they've introduced capabilities, officially TCP binding with the NVMe technology. So it allows you to use to use Ethernet type technologies actually for this NVMe type fabrics. And there's a number of people working on products with those concepts now. This is actually from last year, but there's companies like Mellanox, which is just being bought by NVIDIA now, right? It has a SoC for accelerating NVMe over fabrics. They've actually, this is from last year, they actually made advances on that now. Another company from France called Calray has NVMe over fabric target controller for enabling these just a bunch of flash and other types of technologies. And there's a number of introductions of NVMe products which are starting to ramp up. Still more expensive than SATA and SAS, but as the volume goes up, their costs are going down. And also looking at building this out in the fabric. So this actually is from yesterday. I stuck these in because I thought they were interesting. It was NVMe Developers Day. Another thing's been going on is ideas of reducing the movement of data, okay? And especially to take the burden off CPUs, the central processing units. And so there's a big movement in general in the computing industry, and it's also in the memory space, where people are looking at using what they call accelerators, which are small processors distributed in different places to try to create better overall system performance. And one of the ideas here is computational storage. So SNIA actually, Storage Networking Industry Association, the SNIA, defined following: computational storage device is a component, say a drive, provides persistent data storage and computational services. And I'll show you some examples of that in a minute. And they call it computational storage processor, which is a component that provides computational services to a storage system without providing persistent storage. And then they've got a computational storage array. It's a collection of computational storage drives, computational storage processors or storage devices combined with a body of control software. So this is ways of trying to get to a place where we're not moving data around as much, trying to process data close to where the data is. Okay, and the consequence of that, getting faster results and taking some of the overhead off of CPUs, which aren't growing as capable as they used to be. So here's an example of this computational storage devices. So there's NVMe-based computational storage devices. There's operating systems. This is some of the things we're talking about for building these things with the NVMe. Some examples of these kind of products actually. Samsung last year introduced what they called a smart SSD that actually has a Xilinx FPGA chip as an accelerator built into the drive, and there's a few other companies that have introduced products like this. So anyway, this is just an example, as say from yesterday, some of the things that are going on in terms of computational storage. And I thought this is an interesting chart. They're talking about different ways of doing this computational storage. FPGA outside, working with multiple SSDs. That's that one on the far left, where I've got FPGA and an SSD controller as two separate packages in the device, working with the device. And then where I've got an FPGA only, which does both functions, or sorry, all the way to the right, where I do a single ASIC solution. So there's which does all these functions together. So this is probably ways in which some of these things may evolve. Not every SSD maybe would have this functionality, but it's one approach to doing it. Another approach is actually what they call these open channel or Denali device, where they actually have, it's more the FPGA to multi-SDD approach they're doing there. All this is kind of approaching towards something that's kind of a holy grail in computing potentially, which is memory-centric computing, where I basically don't move data around at all. I try to process it as much as I can in place. Now, eventually perhaps that can actually be done with memory. One thought is it'd be done with some of these new memory technologies can also serve as logic units. People talk about spin-based logic units directly associated with an MRAM storage, a magnetic random access storage device, for instance, as a potential where this could go. There's also things intermediate to doing there. So there's a general tendency for disaggregating all sorts of resources. One of the biggest trends people are doing. So the idea of, the idea is can I move my processing close to the memory? So this computational storage is approaching that. There's other things that are going there as well, memory pooling and sharing. And then these various heterogeneous computing technologies where I stack a bunch of chips really close to each other is another approach to getting there, or ultimately even dividing devices that share memory and processing. So getting onto some of these storage system things, NVMe storage for edge and data center. So it'll be, basically, it looks like NVMe storage interfaces will be the basis of future storage systems. using flash memory and other types of persistent memory technologies. In fact, there was even talk at the Developers Day yesterday, maybe ultimately they'd want to have NVMe hard disk drives, just because then they just have one interface, right? They're actually, WD actually announced in their Open Flex platform, they actually have a hard disk drive enclosure with NVMe on the outside of it, so there's things that are kind of going to that. So you got network storage capabilities, and I can do this remote direct memory access that's built into the NVMe capability, and then Fabric's running on the NVMe protocol. And there's products currently available running over fiber channel InfiniBand, now TCP/IP Ethernet type applications. So this again is from that WD day, because I had a bunch of interesting slides there. And they were showing SSD revenue by interface. I'm sorry, this is really small. It goes up to 2022. It's also kind of dim. I took this with my photograph of my phone. What it's showing is the far left there is SAS, the blue thing to the left for each year, like 2017. The orange thing is SATA, which you can see 2017, that was the dominant interface. And then NVMe is the one just to the right of that. So if you look here, as you go from the left to the right, 2017, 2022, that blue on the far right, which is the NVMe, is seen to become the dominant interface technology going forward, probably killing SATA, essentially, at least for SSDs. This is an example of that Open Flex platform. The thing I was going to mention there, just one example of one of these NVMe type Fabric technologies, and they had the NVMe interface for a hard drive box as part of it. And all this fits into some of these ideas, composable infrastructure, which is becoming very popular and is sort of the latest fad in data centers. Composable infrastructure, I can put things together sort of as needed basis. And composable, decomposable infrastructure. And part of what they're talking about is using NVMe over fabrics to do this kind of thing, and this could include compute and storage memory on the same fabric, therefore enabling you to get some of these computational storage type approaches where I get the processing closer to the storage units, and therefore freeing up the central processor and the overhead on that. And one last thing here on these traditional memory things is just some storage capacity estimates I've got for LTO tape, SSDs, and hard disk drives. And so the growth of processing of data will lead to more storage of all these things. The fastest growth here is actually the SSDs in terms of the total number, although still the vast bulk of things that are stored right now, and for at least the immediate future, will still be in hard drives, because most of that stuff is not accessed that often. But the immediate stuff will be on hard drives, and there still will be some people using tape. I think IDC actually has even more tape. They're probably thinking that hard drives won't make that energy-assisted recording, and therefore tape will eat them from the back, somewhat from the back end. Now let's talk a bit about the new memories, okay? So MRAM is magnetic random access memory. That was a bunch of acronyms. PCM is phase change memory. 3D crosspoint is an example of that. RRAM or RRAM is resistive random access memory. And then this FRAM is ferroelectric random access memory. So there's a bunch of these technologies. The volatile technologies that we've had for a long time for real memory is DRAM and SRAM. And there's products now that are in production. They're non-volatile, NAND flash, NOR flash, MRAM now, and also ferroelectric RAM. And there's early production, actually not so early anymore, on spin tunnel torque MRAM, which is a different, a more compact magnetic random access device. And then, of course, the 3D crosspoint example of phase change memory. And then there's emerging technologies like resistive RAM, things like carbon nanotubes, and a lot of others. In fact, there's a huge panoply, a real smorgasbord or Cambrian explosion of different memory types that people have been playing with. So why this is necessary? Flash can't scale with process advances. Especially, NAND flash went to 3D at 15 nanometer, just shrinking stuff doesn't work anymore. 3D is not cost effective in a CMOS logic process right now. NOR scaling stops with FinFET. That's one of the proposals here. So 28 and smaller processes need something new. That's one of the issues here. low DRAM densities load down the memory bus, and AI is expensive on a von Neumann machine, and that's why people looking at neural networks and other approaches, which may be new computer architectures they might use for these things, and memories are going to be an important part of that. In fact, for some of these neural networks, they're actually using memory technologies. So some of these, there's intense effort to commercialize several memories, could replace current volatile memories. Perhaps SRAM is probably pretty clear that's going to happen eventually, and DRAM eventually. If the volume gets up, it could be possible. These technologies can apply to stand alone, that's supposed to be not along, memory chips, as well as in embedded memory, and could reduce energy expenditure in batteries, which are using, for instance, DRAM, which you have to refresh all the time. Therefore chews up energy, and enable IoT devices as a consequence of that. Also important at data centers at the edge or in the cloud, where also energy use is important. And so there's these, as we mentioned before, there's these different memories that are important for this. So I won't be able to go through all of this here, but if you at your leisure, you can peruse this chart, but it's comparing SRAM, DRAM, NOR flash, NAND flash. Those are established memory types, and looking at some characteristics. Is it non-volatile, the cell size, read time, write time, the endurance characteristics, the energy it takes to write, and then the voltage for writing. Compared to some of these emerging memories, which are ferroelectric RAM, resistive RAM, the older toggle MRAM, and the spin tunnel torque MRAM, and then finally phase change memories. This is actually from the report that Jim Handy and I did. As mentioned before, there's a whole bunch of different things out there. It seems like every few weeks there's a new memory from some school somewhere. Carbon nanotubes, graphene, conductive electron RAM, CE-RAM, polymeric ferroelectrics. They're actually talking about doing that for flexible circuits, so you can have a flexible memory. Ferroelectric tunnel junctions, ferroelectric FETs, interfacial phase change memory, TRAM, magnetoelectric RAM, MRAM. This guy I think at UCLA was doing stuff on that. Racetrack memory was another of these things that was talked about. And actually I saw somebody not that long ago that seemed like they're resurrecting that idea again. That's essentially having moving along magnetic domains and using those as memory devices. So things that are actually out there right now is MRAM and the phase change memory, phase change RAM. Everspin is a company in Arizona that was a spin out from Motorola many moons ago. They've shipped over 70 million MRAM chips. Okay, these are standalone chips, generally not very big, but they're fast memories, they're non-volatile. And they use them for a lot of caching and buffering applications in many different places. They did a partnership about 2.5 years ago or so with Global Foundries. This is one of the big foundry companies. They're building 300mm wafers, and they're supplying wafers for Everspin for their chips, but they're also looking at doing an embedded, they're actually they're going to use these for embedded memory applications. Also Samsung and basically every other foundry, all the foundries have said they're planning on shipping spin tunnel torque MRAM product samples either last year, some have already done it, or this year. Okay, so this is emerging, seems like a very interesting topic. IBM was showing an Everspin MRAM write cache for an SSD at the 2018 MRAM Developers Conference, for example. Now the phase change memory, that's the Intel Octane, for example. They began to ship the NVMe-based SSDs in 2017. Microns keep saying they're going to do it, but I guess they decided they didn't want to lose money on every chip, so they haven't done it yet. Intel introduced their Octane DIMM products in June 2018 with talking about them actually being available, running on the memory channel by next year. I'm sorry, this year now. Our report, we're saying that we think products like these, and maybe some of these other things, could exceed the $6 billion market by 2028. And here's another idea of a fabric. In this case, this was Intel, and they're talking about having their Octane memories essentially playing a role as a fabric from fabric between the processors, and actually being able to share the memory between the processors and the fabric. So this is kind of an interesting direct load store access from one processor's memory to another processor's memory. Actually, they can act like they're each other's memory. So interesting idea. Some other things that have come out recently. This actually, I actually saw this at the CES show. but it was introduced originally in November 2018. TSMC built an AI accelerator chip for a company called Gear Falcon that has 40 megabytes of MRAM. Okay, and it's used for inference engine waiting function storage. And the reason why they did that is to replace SRAM, which takes up a lot of real estate. It's like every SRAM cell is like 6 transistors, so it's really big. And so they went to MRAM to save space in this thing. They were using this for image, examples would be image classification, facial recognition, voice identification, commands, teach the specs. They were showing an application where it actually was working with street lights in Japan. They had some folks that were going to work with them for actually communication street lights. Here's another interesting thing that came up. There's a company called VAST, which like a couple of weeks ago introduced what they call their universal storage. And this is one of the first applications I saw that actually is using the Intel Octane NVMe for more than just like a single device application. What they're doing is a write cache with the Octane storage, and they're using quad level cell flash memory, which has very poor endurance underneath of it. In fact, they're even talking about using consumer grade flash, which doesn't have very good endurance at all. And what they're doing is they're reducing the write amplification by basically, they're writing about the same time they're doing the erase of the pages. And so they're storing enough data in this write cache to be able to write sequentially all at once onto the flash memory as a way of being able to make their storage system object-based, NFS or object-based storage system. So an interesting application. We'll see how well this thing works. And being able to work with multiple units, create a global namespace. So looking at timeline for change for some of these technologies, so traditional architectures, von Neumann architectures, logic, there's gradual changes in that. NAND flash, perhaps RRAM has been, resistive RAM has been talked about as something that could replace that perhaps sometime in this next decade. DRAM, maybe MRAM could replace that sometime. If the volume goes up, the cost goes down sometime by the end of the 2020s or the 2030s timeframe. And so some conclusions here is that I hope I've given you some idea. There's a lot of things that are creating data. And they're creating data. We need to have various types of memory and storage to be able to use this stuff. Both stuff we have to process right now, and stuff we'll keep for long-term applications. So it's creating demand for both lower latency and power efficiency, and that's driving the solid-state storage, including these persistent memory technologies. The flash memory is kind of the primary memory. Solid-state storage essentially is a primary memory now in data centers. But hard disk drives and even tape potentially are not going away because they're so cheap. Much cheaper if they continue the technology advances to keep that ratio in terms of at least the purchase price of the storage. And so new storage technology architectures as well as traditional storage will provide very interesting things in the future where we have we were talking before about AI. AI potentially, right now it's a fad, but being actually practically and useful and used for all manner of things. And being able to store a lot of stuff to be able to do this, but with all the network and connectivity, we can gather this data, we can use this and make intelligent decisions, things that will help us live better lives, longer lives. Could be used for bad purposes, but hopefully be used for good ones. So I have this report, Emerging Memories, if you're interested in that, and then here's some references. And with that, I'm not sure how long I took, but thanks for your attention. If there's any questions.
Thank you, Tom. That was amazing. What a huge amount of information there. It'll take me quite a while to digest. Did Windsor get the first question?
Oh, yes.
So, as co-sponsor. So, can I see by a show of hands how many of you are a member of any chapter of IEEE? Okay, thank you.
And with that, the floor is open for questions.
Yeah. Oh, okay.
Okay, go ahead.
Give it to him first? Okay.
Go ahead.
Could you comment on the reliability aspect as we go up density? At some point, does reliability become an issue, so you need to store redundant data?
Well, there's a lot of aspects to that. It depends on what you mean by reliability. There's the endurance is one characteristic that a lot of these memory technologies wear. okay, and everything breaks, right? So there's that aspect of it, the endurance or the just general reliability, you know, the bathtub curve, right? But there's also things like the error rates. And NAND flash actually has really horrible error rates, and so they do a lot of bit error correction to be able to make these things work. So actually, that's another function of this putting processing closer to memory. Is it actually might one of the functions it serves is actually making the memory more useful. You know, and be able to help you to extend what you could do with that. Or, for instance, I could use that for rebuilding a device if I've got the onboard memory rather than using the CPU. So there's various types of challenges in terms of reliability. I was talking before about applications. For instance, people are talking about embedded memory and using that like MRAM in a car, right, under the hood. Right, so you can imagine the kind of temperatures that you're going to be dealing with and conditions. If you can make something work like that, oftentimes what you're doing is making trade-offs. And in a lot of these devices, you're making trade-offs between the retention of memory in the cell versus the endurance versus the capacity, the total capacity. And you might, for the sake of one, you may sacrifice another one to the extent that your technology allows you to do that. So there's a lot of facets to reliability here, and it's...
So at the system level, there needs to be cognizance that increasing density, there is likelihood of, at the elemental level, increasing reliability, architecture.
Well, the other thing is, if by reliability you mean how well can I make sure this data goes on to the future, as you get more data, you know, unless you do replications of various sorts and parity checks and stuff like that. So that's another part of this as well, especially at these system levels. But I didn't really get into that here, but that's certainly certainly an important aspect of making these things useful. You gonna give it to Gora? Okay, he's a very magnanimous guy. Go ahead. All right, Gora, yeah.
Two questions. Can you talk about, when you were talking about memory and fabric, I was thinking about the evolution of computing in terms of wearables and fabrics as in clothing.
Oh, yes, yes.
You want to talk about that as we are going to non-traditional computing platforms like fabric?
Yeah, in fact, there's even people talk, there's things that are like Gen Z and stuff like that, where they're talking about a fabric that includes a compute as well. You know, there's another way to get to this closest in-memory processing. There's a lot of stuff going on in terms of trying to build networks that can accomplish some of these tasks to be able to disaggregate and aggregate things the way you want to do it. So that's a big area of interest right now. Does that kind of get at what you're asking about?
I wonder what kind of some of the innovations which are emerging technologies in that area, and where are they?
Well, what's really interesting, I think some of the stuff that's driving this, and I was mentioning it earlier, is that right now the costs of bandwidth in general are decreasing faster than storage and processing. You know, storage you run into slowdowns in terms of you know, how fast prices have been going down. Moore's law has slowed down a lot of at least the speeds for processing, but bandwidth is getting cheaper and cheaper, which allows us to do a lot more distributed stuff potentially. Allows you potentially to do more things at the edge, enables some of these IoT applications, depending on what level you're looking at, you know. So there's some really interesting stuff going on here enabled by fabrics in general.
So that leads to my second question is, we're talking about the $9 billion fab industry that I presume there are only 3 or 4 remaining in the world today, right?
There's 4 complexes of fab right now, but going to be 5, or starting to be 5, okay? There's Samsung, there's WD and Toshiba, which have a joint fabs. There's Micron and Intel, which are becoming not joint, right? And then SK Hynix. Did I miss somebody? Intel. No, I got Intel in there. So.
And none of them are in the U.S., right?
I think Micron is. Yeah, at least some of their stuff is in the U.S., but they also have stuff in China too. So a lot of these are Korea or China or Japan.
Which is my unanswered question, or the question I'm not asking. That is a concern as we have more and more sort of demand.
Well, for that matter, there's also what is it, China 2025, there's actually a big effort to try to build these, build both DRAM and NAND flash fabs in China right now. They're putting, gobs of money into that. So, yeah, this
Most of the Intel United States, I believe that.
is Intel?
Yeah, I believe the 3D points manufactured in Mexico, actually.
Is it? Okay. I know there's something in Lehi, Utah, but that's Micron, I think, isn't it?
Micron is in Boise, Idaho.
Micron's in Boise. What's in Lehi?
Micron was going to open a place in Lehigh, but chose not.
Oh, they didn't. Okay. Okay.
I'm good.
But there's a lot of it that's in Asia. Most of it's in Asia. And it's the biggest, actually the biggest investment overall has been Samsung in Korea. Korea's made some of the biggest investments, even more than China, although China's trying to catch up. How about way in the back there first? That's you.
So way at the other end of latency and cost scale, I'm surprised that tape is. I was a product manager for digital audio tape backup device in the 80s. We had 2 gigabytes on, an adapted digital audio tape device. Backup. Changed a lot, but it was always somewhat unreliable. That was a cassette. Where is tape being used now, and is there improvements in things like magnetic tape so that it's, is there anything going on there? I don't expect there may be.
So when you get into that,
Certainly the least cost.
it's the lowest cost storage. That's what drives the interest in it. The most popular tape format is LTO. There's still a couple what they call enterprise tape formats. One is IBM, and then Oracle kind of sort of has one still. But LTO is the majority, and right now they're up to 12 terabyte native in the LTO 8. And then they always give a compressed number on top of that. So they're really big and they're really cheap. The storage cost in these new versions of tape is well under a penny per gigabyte. Under 10,
Is it government things like telemetry, things that may not be accessed that you may want to get at some point?
Yes.
What kind of stuff is being stored on tape?
Well, so there's stuff that you think still has value. Let's say I have to keep records for compliance purposes, but I'd want to save money, right? Or I want to keep medical records that are 10 years old, but I have to keep them beyond the life of people, right? You may put those on tape, for example. So also, another thing that's popped up, some of this malware, people have talked about tape, this offline tape in particular, where actually physically don't put it in a library, but put it on shelves as being an air gap from the net. Yeah. So there's it's hanging in there. There's not a lot of. There's the LTO consortium has 3 members right now. I mean, they have more if you include the tape guys. But there's like I think IBM or plants associated with IBM make all the drives. IBM, Quantum, and HP sell tape drives, and then Fujifilm and Sony make the tape. Yeah. Oh, sorry. There's one over here first. Sorry. Yeah, you. Yeah, blue shirt, yeah.
On the topic of moving the computation closer to the storage itself,
Yeah.
I'm aware of 2 main types of computation, compression and redundancy with RAM formats. It looked like in some of your slides, or at least one of your slides, you had mentioned zlib, which I think is related to compression.
Yes, that's right.
How much conversation is there about doing that to where maybe the CPU is expecting compressed pipe directly from the...
That is one of the things being talked about.
And also, what about, has anyone been talking about RAID configurations where, we commonly think of it as being several disks that are redundant. Is there any talk about maybe making a redundancy to a single device where a single hard drive, for example, we can have a certain RAID number just in and of itself?
The problem there is that things like hard drives don't fail in a part of them.
Right.
Right.
Right, but there's other things like...
So the RAID would kind of, you kind of wouldn't buy, I think you wouldn't buy anything in that. But there's certainly things you can do inside of the, if you had processors inside of a hard drive or an SSD, for instance, I could rebuild after a failure using the drives talking to each other versus going through the CPU, for example. That's one application, one direct application, or management of the content they've got. If they actually were aware of their content, you could do searches on them. You could index data as it comes in and make metadata out of it. You could do compression, drive to drive, things like that. So there are things you could do that may take some of the burden off of a CPU by having these devices. The trade-off is they cost a little more probably to do it, so you have to have a reason for doing that. And where do you put the intelligence? Put inside of each device, or do you put it outside, controlling a few devices, that sort of thing? Is it sort of host controlled? What's the host control versus the internal control? Because a lot of especially the big guys like to tune things their own way. They have their own special sauce in how they do stuff. Let's see, get you first, yeah.
So a few years ago, quite a few, I was working on a project and it was at the university. I got to keep a copy of the stuff on mag tape. Where the hell can I go get a mag tape read these days?
What kind of tape was it? A big reel?
That was the mini reel for the IBM.
There are people that still keep those things.
Yeah, me.
No, but I mean keep the hardware.
Oh, okay.
So there are people, you could probably look on the web and find folks who could read that for you.
Okay.
Now the interesting thing about something like tape too, and true also of optical, is the actual media can last a fairly long time. That's another reason for keeping that is, I think tapes, the thing you worry about a lot of times is the format obsolescence. Can I find the thing to read it? But the actual media under the right environmental conditions, like in a cave, could last for 30 years or more. In the optical stuff, they're talking about lasting for 100 years. It's just, can you find an optical reader to read it 100 years from now? Is there still a USB, thing to plug it into? It's all that. It's all those obsolescence issues you worry about. Yes. You're one of the sponsors, aren't you?
Data cloud, central storage. The ability to remove a lot of redundant data. For example, let's say you and I both like the same album.
Yes.
We both have it on iTunes. Or everybody in this whole room has the same album they like. iTunes only stores one copy of it.
And you just point to it. Well, you may need to make local copies if you're trying to play at the same time.
Right.
Yeah.
But I mean, in the cloud, and you can do it on a block by block basis, where perhaps the data you stored has got some similar blocks as the data I stored, and you remove the redundant blocks.
Well,
Is that making a big difference in the amount of storage?
it does help, and that was another thing that these vast guys are doing. They're saying they have this very deep analysis they do of the content. They had a compression algorithm they thought compressed better than anything else. There's another one of the things they're talking about to get really efficient storage. So so I think the more processing power you have in places to work on stuff, the more potentially things you can do with it. It's like HEVC was H.265 was enabled by being able to get big processors that could process this stuff and turn it into this relatively lossy but relatively good quality content, but it takes a lot of processing on the front end to do that, a lot less on the decoding side. So, the processing capabilities enable us to do these things. And now, with all these distributed processors, it allows us to do a more dispersed kind of capability. And now, they can be ARM, they could be, what was you wouldn't really use it for that, but at the GPU, that was the Nano, they just introduced a new chip for $99 for doing robotics and other things. Anyway, that's kind of off the topic, but there's a lot of stuff you can do in the cloud or even in some of these device and system technologies that can take advantage of your processing to try to, for instance, manage your data better and get a more efficient utilization. That's a big application for AI in general, I think, is just even managing data. I got one. Go ahead.
Yeah, I run an AI lab and building our AI systems, we had to overcome a lot of the problems you mentioned.
Yeah.
It was awesome. And watching what you just talked about and the technologies that are coming, it seems very timely. But one of the biggest problems we deal with in an AI system is the huge amount of data that it generates.
Mm-hmm.
Only a small percentage of that data, though, is useful.
Mm-hmm. Mm-hmm.
But the problem is that it basically, when we generate that vast amount of data.
This is learning. This is for the learning part in particular?
No, this is for cognitive computing.
Oh, for the inference type, okay, okay.
So, yeah, I don't call the other one AI. I don't consider that AI.
Okay.
That's just automated pattern recognition.
Okay.
And it's a fad. But the point is that we generate a huge amount of data. Then the problem is that data clogs up the system because you have to essentially process that data back into a searchable, indexable structure. Anyway, what would really help, and I think you alluded to that, but I just want some clarity. What would really help is for us to be able to have what I would call programmable memory controllers. Because the problem isn't really memory, it's a controller. And so we experimented with creating our own FPGA and putting our own memory blocks behind it.
And actually, the cloud, you can do that now. You can rent them out, you know.
So inside the FPGA, we were trying to take the data and trying to pre-sort what data actually is useful. So what's the point of dropping data into the RAM only if you're going to throw it away? So the problem, I think, is not that the RAM has to get faster, but we just need to be more intelligent about how we use the RAM.
And so putting some processing capability in front of your memory could be a,
The CPU's done its job, right? CPU's generate said here it is. But if we had a better control over how that data then gets into memory, and specifically if memory controllers can then have shadowing capabilities, because once the data is generated by your generator node, the data has to be, again, processed and maybe even archived.
so you're talking about like keeping logs and things like that?
Yeah, you want to be able to have the ability for the memory controller to be able to shift the data near instantly between nodes. Like you were talking on one of your slides about CPUs sharing memory.
Yeah, there was that one that I think one of those slides showed that. Yeah. And so and that's getting into fabrics for the memory and the processing in the single fabric. To enable you to do a lot more of that kind of thing.
So how far away are we from being able to get a memory? Right now, memory is so tied into this system architecture of most PC systems. It's really depressing, right? You want memory to be able to almost be its own thing with its own programmable controller, so that then it can be fabricated out and all that abstracted out from what the CPU really does. So how far away would you say are we from being able to have that either accessible through NVMe or whatever other interface?
I think at an early stage, we're just a few years out from, I think, starting to have those kind of capabilities, at least approaching the kind of capabilities you're talking about. And then, of course, as soon as you do that, you'll fill the pipes up again, and then it'll get hard, but because we're generating more and more stuff. But I think we have to do that. It's kind of if we're going to make this data useful rather than just a big garbage bucket.
Like in our experiment, we saw that just putting the FPGA in front of the memory became all of a sudden not the limiting factor.
And you saw some of these speeds, those memory speeds, they're not the bottleneck anymore. Yeah, and that's why, putting a fabric and mixing a lot more processing in with the memory, I think, is approaching that. Now, do you do it in this computational storage approach, and then you do them connected together, or is it like this open channel or something, or some other approach?
Programmable controllers, then you can decide basically away from the main workflow, whether you want that data to be stored in a database, whether you want to move it around in memory for cache, whether you want to move it into a persistent hard drive, you want to move it onto tape. It should be a decision we can make downstream, not upstream. Right?
Yeah, like I say, I don't think we're very far away from having some of those capabilities, which I think will help a lot. And then you'll just make more stuff and it'll get harder again.
Yeah.
There's always a bottleneck somewhere. Way in the back.
I have a few questions, but one deals with what are the possibilities?
That's right, you didn't get your chance yet. Go ahead.
What are the possibilities of light being used as a storage?
Oh, as storage.
In terms of having, say, fiber optics or similar mediums, and actually do the storage in the optical.
So people
That was something that was taught when I was undergraduate,
yeah.
and now we're talking decades, and we're still kind of thinking about it.
Well, if you go back to the early days, there's all kinds of things people use for memory, like delay lines and, cathode ray tubes and stuff like that. I mean, so So photonics is definitely being used in communication. There's people doing a lot of work. In fact, I just saw last week at the OCP conference, they're talking about tighter integration of photonics with electronics, which is a really big issue, for making these really high-speed networks. And so there's a lot of stuff going on there. In terms of using light for storage, there's a lot of people it seems like everyone and their brother wants to do something in memory or storage. So there's people that talk about, I think there's an outfit in England that's talking about making a really high density inside of a glass-like disk, for example, right? But they're doing like three-dimensionally inside the disk. They put Bibles and books on these things and stuff like that. So there's, and which potentially, it's pretty organic, it probably lasts forever. The other thing I've seen like that is people talking about DNA, and storing stuff on artificial DNA. There's stuff like that around there too. So there's like 1,000,001 different ways in which we could do these things. There's some research money for people to do a lot of these things. There's some stuff that looks like it probably has better odds than others. Using light moving could use a good delay for data, but I'm not sure it's a good or a cost-effective storage media per se. Maybe Bose-Einstein, some of those really cold atoms would be kind of cool, but again, they're kind of not very cost-effective.
Now going back to the more mundane, the issue is of, for example, transferring between the media.
Oh, so for moving data?
For moving data, it's like move it away from tape, for example, magnetic tape, because the data is old, but it's, for example, in application like geothermal plant, where you have some deterioration of the physical structure. It could be very useful to have the new data, old data, and actually have this big data set for analysis. The problem is different media are being used at different times.
And you're saying if all the data was together, it'd be easier to process stuff.
Probably migrate from the, say, tape or the hard drives to some other, to upcoming media. Now, how difficult is it? What kind of issues are we looking at?
So the big issues actually in making decisions on what kind of structure you're going to have to deal with data is you're usually trading off performance and cost, right? And how much stuff I've got, and how much it takes to keep that, and how fast I want to be able to process it, and what I want to process. Those are all the big issues, on how you build systems, with different, and that's what's led to use these different types of memory. Oftentimes the older stuff is older for a reason, because it's not used very much, and therefore they feel justified in putting it on slower storage. They need to keep it for compliance purposes. It's legally they have to keep it or something like that, but they don't want to have to pay for it. So tape, you do it once, you put it in a cave, you pay some really low cost of renting a cave to put it in, and then you probably never read it again. Maybe you will, but probably not. And or you put it in the cloud. Other people put it in the cloud, right? But if you ever want to get it out of the cloud again, then you pay. So there's, but those are the big questions in general, is how do you do stuff to accomplish the things you want to accomplish? And depending upon what your objectives are, that drives your decisions on what kind of a system you can do. Objectives and resources. How much money do you got? What do you want to do? What can I do to make that possible? And what's available today to do that? So, those are the big questions in building all this stuff. On the other hand, storing in light is interesting, but I'm not sure how you do that except that you trap something somewhere, as a consequence.
Exactly that idea that was discussed like 40 years ago.
Yeah.
I was curious what it looks like.
Thank you. There was one way in the back there. Yeah, brown jacket. I think it's brown, isn't it? That's you.
Tom.
Yes.
Just an observation, maybe a question or two. A lot of discussion about sort of parallel architectures here, storage, computational push down the storage, and it just feels like we're doing a full circle back to the 70s and 80s.
Or even earlier. They're talking about going before von Neumann, right? Yeah, 47 or something.
Like, I'll put a peg in there, like 1985 time frame. There was a database company called Teradata that came out and said we're going to put, essentially I/O processors on the disk drives to be able to speed up, what they were doing from a database perspective. obviously, even before that, there was, look at mainframes that had specialized processors. So my question really is, what metric is really driving this return? I mean, I'm thinking that it might be metrics like, IO ops per bit. Looking at the amount of essentially IO you could do in a system. Clearly, there was an era where we were IO bound on disk drives, and flash storage has changed dramatically. So I'm wondering if there's some ratios on that, or on the fabric throughputs that people have looked at and said, okay, here's what's happened historically, and we're kind of back into a sort of a regime where there's now this interest is justified because of these things.
Well, I think there's, that's sort of a number of things I was talking about kind of get into that, is that, we've got to slow down on processing capability. So instead of building bigger and bigger processors to do everything, people are building a lot more little processors and putting them all over the place. And they still have some of the big ones, but they're trying to, because they're not getting faster and faster all the time, they try to offload and do stuff elsewhere. So that's been a big driver for FPGAs and ARM processors and all kinds of things like that. At the same time, the network costs in general have gone down. Long distance in particular, have gone down a lot. It's got a lot cheaper to move stuff. So that's enabled a lot of traffic possibilities, And as you said, now we have these solid-state storage devices that are capable of very fast performance, and so they're not the bottleneck. And what people end up doing is they will take advantage of whatever works really well for right now, until that breaks, and then they'll go to the other thing that's working really well and take greater advantage of that. And what that leads is it's not silly at all to ask the old questions. Why can't I do this? Like, why can't I store stuff in a delay line or a light beam or something like that? Because someday that might actually make sense. Right? At one time they thought it might make sense again. So, these things may be silly, but they're also just ways of thinking in unusual ways, and maybe seeing something that allows you to get beyond whatever our current restrictions, like Einstein's old quote or something, being able to get out of the problem which you thought yourself into in the first place, right? Is by thinking in new ways and looking at stuff in new ways. And we constantly have to do that because we keep changing the technology and make new ways of enabling make new things that become the problem, and now you have to overcome them and find a way to do something new, which makes great opportunity for startups and making money and making more new cool stuff, right? And keeping people being able to get new jobs and find things to do careers in, in engineering, which I think is important. Yes.
Numerical geometries, different geometries, rather than planar or critical geometries, about memory in spherical state.
A spherical memory? So the big problem is connecting up with stuff. So how would, most of our stuff is built like rectilinear, so a spherical connector is not something we do a lot of. You'd kind of have to invent new types, unless you're using light, maybe that's where you use the light beams.
And second is how about organically growing memories?
Oh, organic. Oh, yeah, DNA. So DNA, there's a few companies that are talking about using that for archiving of data. So that might be the thing that eventually kills tape, maybe, is synthetic DNA, perhaps. There are people talking about that, but who knows how long it'll take. But I know there's people working on this stuff, and so there's, and like I said before, there's a lot fewer people that seem to get the innovations in processing and networking, and a lot more of on ways to store stuff. Because creating double states or something like, or multi-level states seems to be something that people find a way to do in all manner of different things. And they say, voila, I have a storage device, right? So this is one area where I think it is incredibly interesting in all the things that people think of as ways of keeping data, which I think is part of what we are as human beings. That's what we've done. That's why we learned how to write, so we could pass things on to the next generation and stuff. And it's this kind of intrinsic thing that people do, that they want to be able to keep stuff. And we're just finding more and more ways of making stuff and keeping stuff. On the other hand, is that stuff, if we had a technological downturn, would it last? It's the whole obsolescence actually causing a dark age or things like that. There's stuff like that that are possibilities as well. Yes? Was there one over here?
No, not really, but I will say, when you talking about tapes, I was thinking of 7 contractors.
Or maybe the 8-track tape in your car? No? You're talking about the old data tapes. Yeah.
The old 12-inch reels.
There's people that still have readers for that. There's people you can hire, you know, I don't know how much they cost, but you know, this, I will confess something. So I had, it was about 2007 timeframe, but I had some data that was about 10 years old I need to find. I had every computer, I think 15 years old, I had every computer that I had with all the drivers for all the storage devices that I'd stored on, whether it be zip disks or Cyquist cartridges, floppy disks, optical disks, old hard drives, parallel SCSI hard drives, all kinds of stuff. I had everything there, and I was sort of been able to migrate most of my stuff, find it, and actually migrate most of my stuff by going from one computer to the other, because I still had all the old computers. That was my my path to deal with the technical obsolescence. There's people like that in even bigger garages, I think, that can help you with those old tapes.
Well, I think that's a great place to end. We're kind of out of time. Let's thank our speaker again.